was a good one. That was a good one.
Don't say chemistry.
This class is boron, so I guess you're just gonna have to solve through it.
Oh, I got it.
You got it.
We went to high school and we had chemistry teachers.
And they said stuff like that?
No. I've never had this kind of experience in a classroom.
I don't know if that's a good endorsement or not.
Take it how you want.
Take it how you want. Okay. All right, everybody, let's get started. Okay, so I checked, I think it was yesterday, 5.1 was still being graded. I don't know if it's graded yet, but I do know the solution's posted. I didn't check it this morning because I've been in back-to-back this morning meetings and whatnot. One thing I'll say about the solution for 5.1 is I posted the Excel sheet, I posted the PDF of the solution, not the actual Excel sheet, because if you had any errors, I want you to see if you can go back and correct that. I don't normally say that, but I will say that with this one homework assignment, understanding the manipulation of the AISC column curve equations is really important because we're doing it a lot, and so that's really all that homework was about. Today is a day that I hope you brought your AISC 15th edition steel construction manual because we are going to be using it. I've got some, as soon as I say that.
I know, it's the one day after.
The one day. Hold on.
I know you're going to say something.
We'll get through it. Okay, so what we're going to be doing today is we're going to be, basically the entire lecture today is sort of about this table, about table 4.1. But more generally, if you remember in our previous lecture, let me go back to the previous lecture that we did. Let me go here, for the previous content. So, if you recall, last time we had done this example, and we did it by hand, essentially. We analyzed the column by hand. Today, what we're going to do is analyze that column using the design aids that are present in the manual. And for columns, so to be clear, there are actually a couple of design aids in the manual for columns beyond just this one. What was that? Less all the other associate deans at Marshall want to learn about column design. But there are other design aids in the manual. There's table 4.1, there's table 4.22, there's a table in chapter 6. But of all of the aids that are useful for column analysis, and ultimately what we really care about is column design, table 4.1 is the most useful. It is so useful that if you open up the FE reference manual for steel design, snippets of this table are in the FE reference manual. So when you take the FE exam, you will actually have this table available for you. That's how important it is. So, is this not working? Is it not like it? Oh, it's because I clicked away at that window, that's why. Okay, so now in order to analyze with table 4.1, you do still need the same K values that we utilized before. And so you do still need those. Remember to make sure that we're using the recommended values, not the theoretical ones. So that's the ones on the lower row. I do want to at least bring up the equations. We're not going to use them so much directly today, but I do just want to bring them up again. So remember, if you want to compute the capacity of a column directly, so the first thing you do is you look at the column and you assess what is the largest KL over R segment for the column, both along the strong axis and the weak axis. So whichever one's the largest is the one that you're going to use, because what that references is the column's slenderness. The section with the largest slenderness is going to control the capacity of the column, because that's the segment that's going to buckle first. Okay? And then under that segment with the largest slenderness, we compute the elastic buckling stress, Fe, and then we use that elastic term to figure out what's the critical buckling stress. Once we get the critical buckling stress, we just compute the capacity as phi F critical times the area. So once you get that, it's pretty straightforward. To analyze using table 4, or table 4-1, sorry, it's a little bit different. Okay, so if you, we talked about this table last time, but this section of the manual lists the axial capacity directly, so not the stress, but the actual load that the column can carry as a function of the column's length, not its slenderness, okay? Now, what it's doing is it's listing specifically the column's capacity according to the weak axis buckling capacity. So what we're going to do to analyze a column using these tables is we're going to determine the largest KLX and the largest KLY. So not KL over R, just KL. So KL along the x-axis, KL along the y-axis. Okay, and then what we'll do is we'll look up our capacity. Now, if KLY is bigger, okay, I don't care what's going on with the radii of gyration. If KLY is bigger, you know the weak axis governs. So just look up capacity. Okay. So if KLY is bigger than KLX, or if KLY equals KLX, then you know the weak axis governs, just look up the capacity. If KLX is bigger than KLY, what we need to do is we need to compare KLY and KL effective, okay? Compare the two, whichever one's bigger, look at the capacity based on that, okay? Now, what's gonna happen more often than not is that when you are looking up capacities, you're going to be looking up capacities between rows. So you're going to be looking up a capacity for a column that has an effective length of 15.9 or 15.436 feet. And there is no listing for 15.436 feet, but there is a listing for 15 and there is a listing for 16. So what do? You linearly interpolate. And so I have here the expression for linear interpolation. We're going to use it here in a little bit, but I will say linear interpolation is something we're going to be doing quite a bit for columns, so make sure that you're comfortable with it. I know that you all know how to do it because you've done it before. Probably, I know you were taught it a while back. I'm sure you're using it in other classes now, so just make sure you're comfortable with it. So what we're going to do is we're going to go back to the column that we analyzed last time, and we are going to compute the capacity of that column using table 4.1. Now there were two facts that I wrote on the board that I want to make sure that we have in the back of our head when we do this example. Okay, the first was what was the answer, and I think the answer was, what was it, like 958? Is that what we got? 958 kits, something about like that. Okay, it was 958 kits, and then the other thing that we got was that the strong axis governed. Now, the way that we determined that for this column is we just looked at KL over R for each of these segments and compared them all and found that KL over R for this segment was the biggest. We are going to find that the strong axis governs using this method, but we're going to find it a little differently. So, with that, let me go back to the notebook. Let's go back to this column. All right, so I have here analyze the column using method 1, but we're going to go ahead and analyze it using method 2. Before I scroll down a little bit, this is what we did last time. So remember, here's the column along the x-axis, here's the column along the y-axis. So just to make sure that it is crystal clear, this image on the left is looking at the column like this. Is looking at it like this, asking if it's going to buckle like this way or that way. Whereas the image on the right is like this, if the column buckles this way or this way. So there's two different ways to look at the column, the two different bracing configurations that you see right here. So what we found in the first method was KX was 0.8 and LX was 35 feet. And then for the y-axis, remember how we looked at the y-axis and we found that this segment was the one that we needed to pay attention to. It has the largest K value and it has the longest length. Y'all remember that? Okay, all right. So let's just keep that in mind and let's do a little bit of quick figuring. Okay. So let's erase all that. Okay, analysis using method 2. Now remember, the shape that we are using is a W14 by, what was it, 90? Is that the shape we were using? Yeah, W14 by 90, Fy is 50 KSI. And what we know is we know that Kx is 0.8, and we know that Lx is 35 feet. Okay, let's leave everything in feet for the lengths. Okay, so what is Kx Lx? What is that? What's 0.8 times 35 feet? Y'all do that in your head better than I can, because you don't need to. You have Casio FX 115 ES pluses or similar scientific calculators. What is that? 28 feet. Okay. KY is 1 and LY is 15 feet. So that's the segment that has the longest length and the largest K value all at the same time. So this one I can do in my head. And so I've got KY, LY is 15 feet. Okay? So is everybody kind of with me with what I did here so far? Okay. So here's what I'm going to do. Okay? Since KLX is greater than KLY, I'm going to compare KLY with KL effective. Now, and the reason I am doing this is because I am trying to ascertain whether or not the strong axis governs or the weak axis governs. Now, to be clear, I already know that the strong axis governs, but I know that because I've already done this problem. Right now, what I'm doing is I'm assuming, okay, we never looked at this problem. We don't know whether or not the strong axis or the weak axis governs. So let's see if we can figure that out by comparing these, okay? Now, KLY, we already know that. That's 15 feet, okay? So KLY is 15 feet. But KL effective is, we're going to take KLX and we're going to divide it by this ratio. And the reason why we're doing that is so that when we compare these two, we're comparing apples to apples. Remember, last time we set the KL over R in the x-axis equal to the KL over R in the y-axis and solved, and that's how we got that. Now, we are looking at a W14 by 90, which means what we need to do is break out the AISC 15th edition steel construction manual. We need to turn to table 4-1. Because we all brought our AISC 15th edition steel construction manuals to class. I don't know if that's the right thing. And what we need to do is we need to find the 14 by 90 and tell me at the bottom what is the RX over RY ratio. So I don't want anybody ever looking up RX and RY and then computing RX over RY, because you can just look it up. That would be a waste of time. So I'll say over here, for a W14 by 90, and we'll say that this is in table 4-1A. What is RX over RY?
1.66.
1.66. So what we're doing is we're taking 28 feet, dividing by 1.66. Okay, and so what do we get for that?
16.87.
16.87 feet. Do I have a second? Just help if I could write that. 16.87 feet. Okay, so what we've got is we've got KLY is 15 feet, and we have KL effective, which is 16.87 feet. Okay, so by comparing these two, I see that this one is bigger, and this is what tells us that the strong axis governs the capacity. Okay, does that make sense? Okay, now, remind me, again, from the last time we did this problem, what was the capacity? What was it? 958. 958, okay. Sorry, just keep that number in the back of your head. Okay, So what we need to do is we need to go to table 4.1 and we need to look up the capacity based on a length of 16.87 feet. Do you see a listing for a capacity of 16.87 feet? No. But what you do see is a listing for 16 feet and a listing for 17 feet. So help me out. So let's see. 4 KL. Here, I'll just write it like this and keep it simple. 4 KL is 16 feet. What is the capacity of a W14 by 90? So I want to make sure everybody can find that. So you're on the column with the W14 by 90. You're on the blue data, because we're using LRFD.ASD. What's the capacity?
Is it 979?
979. Did everybody else find that?
Say somebody double check these.
Okay, no, that's right. So help me out then. So what is it for KL is 17 feet? 955. So let me ask you a question. Before we even do any math, how are y'all feeling about our last problem? Pretty good, right? Because at 16 it's this, at 17 it's this, we're at 16.87, so we're probably going to be closer to that number, right? We're going to be closer to the 955 than we are the 979. And we got 958, probably onto something. So how do we do that? Well, we do a little bit of linear interpolation. So how do we do linear interpolation? Well, we say 979 kips plus, then we have a big old fraction, right? Change in y over change in x, and then essentially change in x. Basically what I'm doing. Now what I did here is I added this term, but I subtracted the other way, because this will be negative, and whatever the linear interpolation is, it'll be this, I guess, minus whatever comes out here. So linear interpolation is one of those things you can do it a number of different ways as long as you do get the right answer, you know. So what do we get for our linearly interpolated answer? And just to be clear, it might be a little off from what you did in the last method. That's okay.
Not 58.12.
958.1. So we'll say just keep it simple. And you both got the same thing, so it is way faster. It is definitely way faster. Are you starting to see why these design aids are so powerful? Because you can do this stuff very, very quickly, okay? Now, here's the thing. You do sacrifice a little bit of accuracy. You are going to get a slightly different answer for this method than you did the previous one. Because in the last method, you are computing the capacity along that curve. Now, you're just linearly interpolating along discrete elements of that curve. So it's going to be wrong a little bit. But who cares 958 versus 958.1? It doesn't matter, okay? And you're really going to see why it doesn't matter here in a bit. It is a lot easier to understand why it doesn't matter when you start getting into design, because there are only a discrete number of shapes from which you can pick from, so there's going to be conservatism built into your design regardless. So one of the reasons why when we get into column design, we don't really think about efficiency like PU over VPN, because you might have a horrible efficiency but still have the most optimal design. And the only way to understand that is to actually do some column design. So before I move on, does anybody have any questions about this?
Why do you have to do linear interpolation? Like, why would you not just round up, call it 17 feet?
Well, you could. I mean, I guess you could. So, but some of us, that's a fair question. I want to put a pin in that and wait till after we've done a couple column design lectures, and you'll kind of see what I mean. So, because once you get into column selection, you'll kind of get a little bit more comfortable with the answer I'm going to give you. So, does that make sense? All right. Any questions? All right. Don't forget that question, because I want to address that again maybe on Monday. All right. Okay. So now I want to talk about design. Okay, I want to talk about column design. Column analysis is I give you a column, predict its capacity. Now I want you to select a column for a given load. Okay? Now, here's how you do it. Okay? The first thing you got to do is you got to determine your factored load, like 1.2 dead plus 1.6 live, and then you need to determine the largest KLX and the largest KLY. Those two steps are probably pretty easy to understand because we just use table 4.1. Like, you can see why you need those in order to interpolate table 4.1. Here's where things might be a little interesting. Okay? You cannot look up a section based on the strong axis. You can't do it because table 4.1 is written for the weak axis. So what you have to do is you have to look up sections based on the weak axis, and then for each of them check the strong axis. Now, here's what my suggestion is. Based on KLY, based on the weak axis, you need to select a trial group of sections. Okay? And here's what I mean by that. Okay? What you're going to do is you're going to go through the W14s, pick a column. Then go through the W12s, pick a column. Go through the W10s, pick a column. Go through the W8s, pick a column. I'm sure some of you are thinking, why are you only asking us to look at these four families? Well, there's a good reason. Those are the only ones listed in table 4.1. You won't find any W27s or W30s or anything like that. You're only going to find W14s, W10s, W12s, and W8s. But why? Well, here's why. Columns, so first off, W shapes are I-shaped cross sections, right? Okay? And regardless of what section you're looking at, they're going to be sort of an I-beam, right? W sections that are W14s, 12s, 10s, and 8s are the ones that are more square, okay? In other words, the flange width and the depth are about equal, okay? Square sections like that work very, very well for column strength. The reason why is because the ratio of Rx to Ry is usually pretty low. Sections like W24s, W27s, W30s are much deeper. The ratio of how deep it is to how wide it is much higher. So if W10s, W12s, W14s, W8s, etc., if those are column sections, the other sections are beam sections, okay? So the more deep W sections are more aptly used for beam selection as opposed to column selection. Does that make sense? That's why table 4.1 only lists these sections. Okay, now, yes?
Is it based, step number 3, is it based on KLY or the larger of?
No, it's only based on KLY because step 4, we're going to go back and check each one. And that'll become clear as we go through a few examples. So, because we're gonna have some practice on this. Don't worry. So the reason is let me address that. So what you're going to do after step 3 is you're going to have a family of possible shapes. For each of those shapes, you're going to check and see whether or not the strong axis governs. So what might happen is you have 4 shapes, maybe 2 of them work. Maybe 3 of them work. And of the ones that work, pick the lightest one. Does that make sense? Now, I say that you should try and select at least one W14, one W12, one W10, one W8. It's possible that a W8 might not work because or it's possible that a W10 might not work. You might have some pretty heavy loads and there's just no W8 section that works. That happens, okay? In which case, just skip it, okay? Most of the problems that we'll do in the class, you'll have at least a W14, W12, and W10. There are some that you might not have a W8. Again, under some heavy loads, a W8 is only like that deep. You know what I mean? And we've got columns that have 1,000 kips on it. There may not be a steel beam or a steel W section that's this deep that can hold up 1,000 kips. You know, that's not a bad thing. Okay. For each one of those shapes, check the strong axis. Now, what we're going to do today is we are going to practice looking up trial shapes with table 4.1a. Okay? So the problem that we do today is engineered such that the weak axis governs, and all we have to do is look up a section and move on. The problem that we do on Monday is going to be a little trickier because for those sections, the strong axis might govern, it might not. And that one will be a much more involved, more quote-unquote real column design problem. Again, we're taking it slow. We're going to take our time with it, okay? Now, what we'll do is we'll check all these sections, and from all the group of the trial sections, select the lightest one. So the idea is that if you can look at the column and see the weak axis governs, just look up the capacities, pick the lightest one. But if the strong axis might govern, you got to check each one. And so I want to explain how that works with this problem. So we're going to do a column design example, okay? Oh, I'm sorry. I do want to mention one last step, and this is something I think that it's a good idea. Once you get your final design, you should analyze it using method 1. We're doing a lot of interpolation, a lot of guess and check, a lot of figuring to arrive at a trial section. I think it is good practice to step away from method 2 and just do the math and see whether or not the column works. Okay, I think that's incredibly important practice. We're talking about columns that can hold up 1,000 kips. I think 5 minutes worth of math is kind of, you know, not a bad idea.
Is that pretty standard for like an actual engineer?
Yeah, it is. So let me qualify that with a couple statements. So when you're initially doing some design, yes, it's usually common to do some back of the envelope calcs to make sure that the columns you selected works. Even packages like Ram Steel, for example. Ram Steel is a popular steel frame design package. It will produce design calculation reports on a per member basis and do all the math that we're talking about. That's not unreasonable. Yeah. So we're going to design a column today. We're going to design a column to withstand 100 kips of dead load, 200 kips of live load. Ooh, I never screenshotted this into the notebook. Let me screenshot that now. Oops. Let me do that again. That's better. I had done that. Whoops. All right, so we're going to select a column for this bracing configuration shown. So I have the x-axis and the y-axis bracing shown here, and we're going to select the lightest column that we can find to withstand 100 kips of dead load, 200 kips of live load. Okay. Now before we get away from this image here, let's look at a couple things. So, first thing we ought to do is we ought to factor the load. Let's go ahead and do that. Oh, let's go ahead and do that now. So step 1. That should be pretty standard stuff by now. What's the factored load on this? 440. 440. Do I have a second? Okay. All right. Before we get away from this configuration, let's look up. So here's my bracing configuration. If I show you a bracing configuration, what do you think we need to figure out? The K values. We need the K values, right? So how many K values do we need for the x-axis? 1. How many for the y? 2. Okay, so K values, let's see. So x-axis, what's the K value for that x-axis? So we have a fixed boundary condition on the bottom, a fixed boundary condition on the top. 0.65. Yeah, don't use the theoretical, use the recommended. Let's be more specific. Okay, what about the bracing configuration over here on the right? So I've got pin up on the top. What's the K value here? 1. What about the bottom? What's the K value there? Somebody else.
0.8.
0.8. So if I'm looking at the y-axis, which segment do I need to worry about?
14.
The upper one. It's the larger K value and it's the larger segments. I don't care what column we pick, it's going to be the most slender. Okay. For the x-axis, we really only have to worry about the 1. So let's see. The largest, KLX and KLY. Okay, so KX, LX is 0.65 times a length of 21 feet. What is that? And then KY, LY is 1 times 14 feet, which I can do that one in my head, that's 14 feet. So, because of this, because KLY is bigger, what I can tell you is that I don't care what shape we pick, the weak axis is going to govern any day of the week and twice on Sunday. If the opposite were true, if KLX was bigger, I'm not sure I can tell you that with much specificity. So what that does is make the column design a little more intricate. Those problems we'll deal with on Monday. Do you have a question? Oh, okay. So what I can tell you is that this says weak axis governs no matter what column we select. Okay? And again, if the reverse were case, I could not state which axis governs either way because it would be dependent upon the column. Okay. Here's what we're going to do. And we're going to do a lot of page flipping today. So we're going to select trial shapes. And so because the weak axis governs, the actual column selection is going to be really easy, but we're going to take our time with it. Okay. So let's start off recognizing we're selecting based on 2 quantities. PU is 440 kips and KLY is 14 feet. No matter what happened in the previous step, you always select based off KLY because that's what the table computes the capacity based off of. So let's start off with the W14s, okay? So here's what I want you to do. I want you to go to table 4.1, and I want you to start with the W14s. And I want you to find me the lightest section that has a capacity of at least 440 kips when its length is 14 feet. So what you're doing is you're going off that 14-foot row and you're finding the lightest column that you can where the capacity is at least 440 kips or larger. Okay, a W14 by 61. Okay, so let's write that down. Okay, now you selected that because its capacity is what?
Sorry, what?
571.
Yeah,
571. Okay, so we're gonna wait a little bit. I want to make sure that everybody can find that. This is important. Okay. Did everybody find that and see that? Okay, so I want somebody else to answer the next question. Now what I want you to do, give me a W12.
53.
W12 by 53. Now you selected that because its capacity was what?
502.
502. Now, before we move on, I just want to ask a simple question. If I said pick between those two shapes with no other information, no other lookups, which one would you pick?
32 by 53.
And that is because it's lighter. Exactly right. All right, so now we go to the W10. Tell me what W10 we ought to pick.
W10 times 49.
The W10 by 49, okay? And you picked a W10 by 49 because it has a VPN of
471.
479. 471.
Yeah.
Okay. And then the W8, is there a W8 that works? Which one? What else?
58.
58. And you selected that because it has a VPN of
482.
482. Okay, now before we go on and select our answer, I want to be crystal clear on something. I want to show you this. This is a really important observation. If you remember, one of the things I said a second ago was that efficiency doesn't matter anymore. That the PU over VPN, remember what we did for tension members? We said that the efficiency was 90% or better? That's the one that you use? Okay, check out the W12 and the W8. Which one out of the W12 and the W8 would have a better efficiency? The W8, because it has a lower capacity, right? So the PU over VPN would be better. But of the W12 or the W8, which one would you pick? The W12, because it's lighter, right? So, and some of you are wondering, well, why is that happening? The reason is because the column buckling expressions are not linear. They're weird. They're whoop, as Mr. Odell loved to point out my sound effect. But there's some truth to that. They are a function of a nonlinear relationship coupled with the fact that the Rx to Ry ratio for different shapes is not constant, right? So there's variability in how we produce those rolled shapes. So it's possible that a lighter shape has a worse efficiency, okay? And you can see it right here, okay? But all this is sort of moot at this point because of these four shapes, which one would you pick? The W10 by 49, yeah. And so for this problem, boom. Now, let me be clear. I do think that you should analyze using method 1. I want to clarify that a little bit. So what I mean by that is we have Fy is 50 KSI. We know that PU is 440 kips. We know that KLX is 13.65 feet. We know that KLY is 14 feet. And we know we're using a W10 by 49. So there's nothing stopping us from saying, you know, compute largest KL over R, compute FE, compute F critical, and then for compute VPM. All right. Now, I'm not going to make us do this in class today, but for column design problems, I generally think that this is a good idea. Now, I want to qualify that statement. To be frank, for this particular example, it's a waste of time because I'm telling you the capacity is 471 kips. The reason why I know it's a waste of time is because I know for this column the weak axis governs. So whatever I look up in that table, I looked up 471, I guarantee you, go through all this hullabaloo, you will get a capacity of 471. The reason why I mentioned that you should analyze at the end is when the strong axis governs. Because as you're going to see on Monday, we're going to do a lot of different trial selections, and for each of those sections, we're going to do some interpolation and some figuring. When it's all said and done, and there's a lot of different figuring, I think at the end, once you arrive at a trial shape, you ought to check it to make sure. Today, it's really not necessary. And it won't be necessary, I don't think, on your homework assignment, which is due Monday. But for the next homework assignment, the analysis will be very important, okay? Does that make sense? All right, does anybody have any questions about the process of looking up the shapes? That part's kind of important because when we do our quote-unquote real column example on Monday, we'll need to know how to select trial shapes based on a load and a weak axis effective lengths. Sound good? Would you like to get out 8 minutes early? Okay, I'm gonna pull up the code again, but try and stay dry with all the rain, and I will see you all Monday.